The great circle or orthodromic distance is the shortest distance between 2 points on the surface of a sphere, measured along the surface of the sphere. The distance between 2 points in Euclidean space is the length of a straight line between them, but on the sphere there are no straight lines. In non-Euclidean geometry, straight lines are replaced with geodesics. Geodesics on the sphere are the great circles. Through any 2 points on a sphere which are not directly opposite each other, there is a unique great circle. The 2 points separate the great circle into 2 arcs. The length of the shorter arc is the great circle distance between the points. A great circle endowed with such a distance is the Riemannian circle. Between 2 points which are directly opposite each other, called antipodal points, there are infinitely many great circles, but all great circle arcs between antipodal points have the same length, that is half the circumference of the circle, or, where r is the radius of the sphere. The Earth is nearly spherical, so great circle distance formulas give the distance between points on the surface of the Earth correct to within 0.5% or so. Formulas: let n be the geographical latitude and longitude of 2 points 1 and 2, and their absolute differences. Then, the central angle between them, is given by the spherical law of cosines. The distance d, that is the arc length, for a sphere of radius a and given in radians. Computational formulas: on computer systems with low floating point precision, this formula can have large rounding errors if the distance is small. For modern 64-bit floating point numbers, the spherical law of cosines formula, given above, does not have serious rounding errors for distances larger than a few meters on the surface of the Earth. The Havazian formula is numerically better conditioned for small distances. Historically, the use of this formula was simplified by the availability of tables for the Havazian function, Hav, I, a equals a sin 2, I/2. Although this formula is accurate for most distances on a sphere, it too suffers from rounding errors for the special case of antipodal points. A more complicated formula that is accurate for all distances is the following special case of the Vincenti formula. When programming a computer, one should use the arctan2 function rather than the ordinary arctangent function, so that is placed in the correct quadrant. The determination of the great circle distance is just part of the more general problem of great circle navigation, which computes also the azimuths at the endpoints and intermediate waypoints. Vector version, another representation of similar formulas, but using normal vectors instead of latitude-longitude to describe the positions, is found by means of 3D vector algebra, that is utilizing the dot product, cross product, or a combination, where and are the normals to the ellipsoid are the two positions 1 and 2. Similarly to the equations above based on latitude and longitude, the expression based on arctan is the only one that is well conditioned for all angles. From chord length, a line through three-dimensional space between points of interest on a spherical Earth is the chord of the great circle between the points. The central angle between the 2 points can be determined from the chord length. The great circle distance is proportional to the central angle. The great circle chord length may be calculated as follows for the corresponding unit sphere, by means of Cartesian subtraction. The central angle is. The great circle distance is. In this last formula, the central angle must be in radians. Radius for spherical Earth. The shape of the Earth closely resembles a flattened sphere with equatorial radius of 6,378.137 km. Distance from the center of the spheroid to each pole is 6,356.752 km. When calculating the length of a short north-south line at the equator, the circle that best approximates that line has a radius of, or 6,335.439 km, while the spheroid at the poles is best approximated by a sphere of radius, or 6,399.594 km, a 1% difference. So as long as we're assuming a spherical Earth, any single formula for distance on the Earth is only guaranteed correct within 0.5%. A good choice for the radius is the mean Earth radius. In the limit of small flattening, this choice minimizes the mean square relative error in the estimates for distance. See also, air navigation, central angle, circumnavigation. Flight Planning, Geodesy, Geodetic System, Geographical Distance, Great Circle Navigation, Havazian Formula, Meridian Arc, Qibla, Rumline, Spherical Earth, Spherical Geometry, Spherical Trigonometry. References. External links, Great Circle at MathWorld.